Well, good morning. Not that many of you. I hope some more people will show up, but they don't know what they're going to miss. We're going to have some fun. This is all, especially if you had never heard about OpenMP until yesterday morning, then this is going to be a bit of a stretch. I just want to give you a general feeling of what it takes to get good performance and the things not to do. But it's just, that's the big thing. If you remember some things like, okay, I shouldn't do that and do this, then I'll already be very happy. But probably once you have some more OpenMP experience, you go back to the slides and what did he say again? I call this very long title, Speed Up Your Application. The real title is actually this one. It's okay to be lazy. What do I mean with that? I'm a lazy guy. I don't like to do things unless I have to. And the same is true for tuning. You do that with care. That's really what this is. And what I hope to show you is that it's not so much about the effort that you need to take, but more the insight that you have. One of the things I like about OpenMP is you don't have to rewrite half of your code to implement an idea, because it's all a matter of a pragma. You add another pragma, hey, cool, that works. And sure, at some point you may decide that in order to get more scalability, you will have to redesign some of your algorithm, maybe, but this is much more gentle. And that's what I mean with lazy. You just got to understand what's going on. And that's what I'll be talking about. Well, before I do that, I don't know, who was here on Monday with the first session, because then we can just skip this slide. You know who I am. I have a lot of material, so just the one-liner is I work in the Oracle Linux engineering organization, and that's great fun to be in. Unlike most, no, I shouldn't say that. I just recorded. Okay, it's fun to be in. Okay, this is the agenda. I'll have a little bit of a prologue to set the stage. Then I have almost sort of random collection of tips and tricks, things that I saw in applications that were general enough to be worth sharing, because performance is always specific to the case that you're looking at. Then we're going to have a short break. I think an hour and a half talking is too long for people to absorb. And at some point, before we go into the NUMA part, I want to have a short break, hopefully around 10 minutes, we'll see. And then at the end, we have the Q&A. I always find it funny because Q&A suggests that I have an answer to every possible question asked to me, and that's not true, I can guarantee that. I'll do my best. The prologue, I'll do that fairly quickly. You'll get the slides after this talk. I'll make them available. The reason is that I keep on making changes to the last minute, so there's no point in putting the slides up until they're done. This is the website that Christian mentioned that already, openmp.org. That's your place to go. That's where you find a lot of information related to OpenMP. One of the good things about OpenMP is it's old. And the reason is that it's supported by a very large number of companies and institutes, research institutes, universities, but also the big companies that actually make it worth going. Because if you don't have that, then eventually you'll just fade out. And it's quite surprising that OpenMP is still, we still sign up new members for the board. So. Christian showed some of these books. I want to add a little bit more to it. You have them here, so I won't say much about it. One thing, this is an old book, but it's still selling, surprisingly. But it is about the basics of OpenMP. So if you really want to go to the basics, this book may help you get started. Then there's another one, the Common Core. Common Core has made a selection of everything that OpenMP offers, and that's what they think is good for you, and I don't always agree with that choice, but that's what the Common Core is. Then we have the book about more advanced features, for example, all the NUMA stuff I'll talk about, the tasking, things like SIMD, they're all covered in a lot of detail here. Then there's an interesting book if you're curious what happens when you run your OpenMP program, because as I think when you listen to Christian's talk yesterday, so much happens under the hood, which is both a good thing and a bad thing. I think it's a good thing, but it also means that, and I'll show that, some unwanted things may happen. and you don't see them because they're hidden. So it's a mixed blessing. Overall, I like it. And that's what this book talks about. And then if you plan on using GPUs in OpenMP, this is a really good book. You can't read, the problem is you can't read the specifications anymore. You can. There's a PDF with the full specifications, but they're not written for mere mortals like we are. They're written for people that need to implement OpenMP, not the ones using it. And there's a big, big difference. So these books help you more gentle. I'm going to show some pictures of profiling, and I just wanted to mention, because people usually ask me, what are you using? I'm using, and yeah, disclaimer, conflict of interest. I'm involved with the development of this tool. So guess what? I'm using my own, eating my own dog food, as they say. It's called gprof-ng. I'll be very quick. And but in general, I don't care. But you have, whenever you do performance tuning, no matter what you do, you have to use a tool that will tell you what's going on. And whatever you pick is fine with me. Without that, you could be sent in the totally wrong direction. That's the biggest thing. I have had people come to me and they said, well, can you help me with performance? And I know where the time is spent. And unless you show me the profile, and depending on my mood, I may smile or not, but I won't believe you. Because the profile is usually very different than what you think based on your science. For your science, some part is really important, and for the performance, it doesn't matter. And then it turns out that you are setting an array to 0 1 million times. And like, oops, that was not necessary in taking most of the performance. That's why you need to use one of the tools. There are many, just pick whatever you like. This is one of them. It's part of the GNU open source bin utils toolkit. And if you want to know more, there's a starting blog. But this is the kind of stuff that it produces. This is an OpenMP program. And I ran it on 4 threads and 8. And this is a timeline. So time is from left to right, and you see the individual threads. And the first thing you see, hey, it's faster. But of course, when you start digging deeper, and I have a case study on that, you can uncover some bad things that are going on. But the initial observation is, yeah, it is faster. It's scaling. Not all that great, but it's scaling. Okay, that's about profiling. I'll say that a few more times because it's the classical thing. And I know it takes time to get to learn how to use a profiling tool, but please spend some time on it. Tips and tricks. Claim. You can get good performance with OpenMP, and your code will scale if you do things in the right way. And that's where the catch is. In that sense, MPI is easier. With MPI, you basically have your send, receives, and all the flavors. You know that's where things happen. If something bad happens, it has to be in those calls. With OpenMP, many things are hidden, and again, I'll try to uncover some of the most important ones to help you get around that. This is another one. This is my political version. The fact that OpenMP is easy to use, I think, doesn't mean you can write dumb code. And I'll say that again a little later. Because OpenMP is very prescriptive. You tell the compiler, this is parallel, you parallelize this for me, and it will do it. If it turns out that there's almost no work in that part, you'll be killed in the overhead. So in that sense, the ease of use is great, but you're not off the hook. You have to think about what you're doing, which is in general a good thing. So I'm going to cover the basics, and if you would ever need to go to the OpenMP performance court, and you follow these guidelines, the lawyers in there have no case against you because you did everything right, and it's probably the runtime or the compiler. The one thing is, I'm not going to talk about blazing scalability to like thousands of threads, because most people don't have that situation. And usually what I see, the problem already starts on 2, but you didn't see it. And then it gets magnified as you add threads. But very often when you have a performance problem, what's one of the rules recommendation is try to go to the lowest thread count that exhibits the problem, and these profiling tools help you because you can already see the first signs, like, oh yeah, okay, yeah. And it makes your life just a lot easier. You can do small-scale testing and those kind of things. Okay, like I said, you follow the rules, nobody can sort of blame you in that sense. The ease of use, I just said that, is a mixed blessing, but I prefer it over the alternative. I don't like things that are hard to use. But again, there's something we have to be careful with. One of the things I like, if I have the moment from idea to implementation is usually not that long. Basically, you insert some pragmas and that's it. But that's also where it starts. Yesterday, there was a question about what's the difference between the critical region and the atomic instructions. That's a very valid question. Well, performance. How can you know unless somebody told you? The specs won't tell you because they're not written for people in this room. So yeah, those are those unwritten rules that I'll talk about. So yes, there are differences, and you have seemingly you've done everything, you're using a critical region, but then you need to know that the infrastructure around the critical region is much more heavy because you have to deal with a more complex situation than an atomic. Because an atomic is one instruction or two instructions in the computer. A critical region is just a whole block of code. So that's why atomics are preferred. They're faster. Again, if nobody told you, how could you know? And again, if you write dumb code, you most likely will get dumb performance. Just don't blame OpenMP. I go to these conferences and you see people do horrible things with OpenMP, and then they blame OpenMP and not themselves. Of course, there can always be a bug in a compiler, in the implementation, but in most cases you did something wrong. And it's not about blaming, it's just that you may not know what you were doing. I once saw a paper, a blog about a guy who said, oh, OpenMP doesn't scale. What he had a for loop with one critical region in it. Yeah, that's not even parallel. I mean, sure. There was an interesting discussion after that. Step one, find the right algorithm. And Christian knows it, and he agrees. When we talk about Fibonacci, and I know Christian said it about 1 million times, don't do what we were showing you. That's a really dumb algorithm. Sure, it scales nicely, but it's just to illustrate the concepts, but don't do that. Start with the sequentially best algorithm that you can find. Even if it means that it limits your parallelism, you'll probably win in the end, because you start on a much faster basis than when you have some slow algorithms. Slow algorithms tend to scale better. I said that on Monday. That's because you hide the overhead, you mask the overhead, because you spend so much time on your silly algorithm. So do some search, find out what's the best one, and then try to make the best out of that from a parallel point of view. Again, select the profiling tool. And then there's the next thing to look at. Where do you do the parallelization? You can usually find some loops that can be parallelized. Is that the best level to parallelize? Okay, you go higher and do it in a higher level. The higher the level, the less the overhead. And that's your choice. If you have that luxury that you have different levels of parallelization, find the medium ground there. Because, let's say you're working on a 3D problem, and for a while you can decompose that independently, but that would limit your parallelism to 3, which is not a good idea. So try to find something, do that with care. Try to avoid going to the lowest level, because as Christian explained there's all this infrastructure generated with OpenMP. If that's in the heart of your code, in a loop, in an outer loop that's executed 1 million times, you get the overhead 1 million times. So try to go to a reasonably high level. And then use OpenMP and do that in an efficient way. One other thing, whenever you've done performance tuning, you know that it's a highly frustrating thing to do. I could give endless talks how I made code slower. You wouldn't be interested in that, but that's the reality. You have that brilliant idea, you type it in, and geez, it's slower than what I had before. And only later you realize that brilliant idea was not as brilliant as you thought when you came up with it. Eventually you'll win. Maybe you got to drop it for a while. Don't give up too easily, but be prepared that you try something and it may not work. And again, this is also where these profiling tools come in, because they'll help you find out why that brilliant idea was not so brilliant after all. Okay, the basics. A little bit, I mentioned that on Monday already. I'll be quick on it. Caches play quite a crucial role in performance in general, but also when it comes to OpenMP because of the cache coherence. And they're nothing more or less than fast buffers for data and instructions. And in a modern system, you'll find a whole hierarchy of caches, level 1, level 2, level 3 maybe. And some caches are private to the core, and others are shared, and you can have sharing at a higher level. It's a very complex system by now. Most of it you don't need to know about. Most of the general rule is try to keep things close to your CPU, and wherever they are is less of a detail move. So I've done that low-level cache tuning, but essentially I wouldn't go that way. So let's look at a typical example. Here's the core. You have a cache for data and instructions. By the way, we call that level. So level 1 is closest to the core in terms of time, and then you have level 2 takes longer, level 3 takes longer. That's the wording that is used. And as I said on Monday, the unit of transfer is a cache line, a number of elements in a way, like 64 bytes or 128. The problem is there are very good reasons to have short cache lines and there are very good reasons to have long cache lines. So what do you pick? It's always a compromise. And that's also why the size of the cache line may be different from level to level as a tuning in the system. But you really don't want to tune at that level. Compilers have gotten pretty good at that as well. So what we have here, we have 3 levels of cache, level 2, level 3. This is called last level cache, LLC, because it connects to the memory. And on Monday I mentioned cache coherence. I'll do that again in a while. That's where cache coherence plays the major role. Usually these are kept coherent in a brute force way, and here it's a more smarter algorithm to keep the things coherent. And this is what a typical system looks like these days. A bunch of cores, a whole cache hierarchy, and memory. And the rule of thumb is very easy. The capacity increases and the speed decreases, gets slower and slower as you move away from the core. So you want to try and keep things close to those cores. Then we have multi-core and hardware threads. So you have your system, but inside that core, you may or may not have these hardware threads. They basically support fast switching of activities. That's what it does. And here's an example. It's part of the design. Again, some have it, some don't. You can check it. I'll show you later on how you can check it. And they're meant to help the performance in a transparent way. Could be a parallel code or just a general workload. And the idea is your instructions are executed in what's called a pipeline. And you have multiple pipelines in a core. And the pipeline may stall. It will block because it's waiting for something. Typically in the pipeline level, like a cache miss. And that could come from far away. You could easily spend hundreds of cycles waiting. And in that time, the CPU the core would just burn cycles and waste energy, and you won't make progress. That was the observation. So what was done, in order to deal with those gaps, you figure out a mechanism, and it's called hardware threads, or there's other names around, but basically it's some sort of support in hardware for threading, is you quickly schedule another thread or process. Could be at the process level, could be like if it's just a whole workload, but you're not going to be idle. You're going to use that gap, and you do that very efficiently because it's all done in hardware. The OS doesn't even know about it. It just happens. And when you do that, then it can be very efficient, and you can get a benefit, like in this case, you save time. That's the idea behind hardware threads. Every thread, and that's what I'll need when I go to the NUMA part, has an ID in the system. The OS will assign an ID to it, and there are commands to figure out what is what, the numbering. And you'll see more of that in the NUMA part. That's why I put this in, because I'll need it later on. So now let's look at some basic things. Basics for everybody. This seems so obvious. Do not parallelize what doesn't matter, but you wouldn't be the first one to fall into that trap. They start blindly parallelizing everything you see in your code. That's not a good idea. For the reason that I mentioned a little while ago, you may parallelize something that's inefficient. It doesn't matter for the time. It's so fast. And then you add overhead, in this case of OpenMP, or even MPI would even be heavier, to it. That will slow you down. That part will go slower, not faster, as you add threads. So that will offset your gain. Don't do that. Do that with care. You take that profiling tool, The profiling tool will tell you where the time is spent, and at that point, you're basically interested in the percentage. And on Monday, I showed Amdahl's law. That will tell you how far you need to go in order to get a certain speed up. So you tackle number one. Well, if you do a good job, it'll drop in your profile, then the next one will bubble up. So that will go on for a while until you get tired or you feel like you're done. But that's how you do it. Do that with care. Start by tackling the top functions. Another golden rule in OpenMP, the sharing is really nice. There was a design decision in OpenMP 1.0 to make sharing the default, sort of. It's a sharing model. That's really good. It makes it convenient, but not necessarily fast. Because there's a price to pay when you modify shared data. I'll get to that. Reading shared data is always okay. As long as you just read, there's no problem. And actually can very efficiently use your memory. Let's say you have a large table that you need to read, then you just read it once and that's it. And every thread can access it from the shared pool. But modifying it, that's when you got to be a little bit more careful. Rule number one, use private data as much as you can. In that sense, you follow the MPI idea. MPI only does sharing through the message passing. Here you try to, and there was a comment on that yesterday. Unfortunately, I had to leave yesterday a little earlier, but yeah, you use private data, and then at the end, you copy it into a shared structure because other threads may need it. If other threads don't need it, then you don't have to copy it back. But that's a very good strategy because you leverage the private data as much as you can while you use it. And so that's a very simple rule, but be careful with sharing data. Think big. One other classical mistake, and it's so important that I actually am going to have a slide on it with my favorite, the parallel for or parallel do. And one is fine. If you have more and they're back-to-back, it's pure evil. Let me show you an example. And this is what I see in too many OpenMP applications because it's so natural to do. And it's so easy, but it's not the best thing for performance. Here's a parallel for, again, or parallel do with some code block. And then another one, and another one. You just parallelize all these loops in your program, in your function. Very natural, and yes, this will run in parallel, but you're wasting a lot of potential performance gains. Why? Well, first of all, this is a shortcut for a full parallel region. A parallel region is fairly heavy in terms of OpenMP. It's a fairly expensive thing to maintain at runtime. A lot of things going on. A lot of things can happen in a parallel region. So the cost of a parallel region is not zero. So that's one. So these are sort of parallel regions in disguise. They look like a for loop, but are really parallel regions. So compiler can strip out some of the overhead, but it's still relatively expensive. Worse, there's no potential for the no wait clause. And I think that was mentioned yesterday, Christian. Sorry, the no wait clause was mentioned. Okay, good, thanks. So it's all about efficient parallel programming for shared memory is a lot about barriers. Barriers are needed for correctness, but they're very disruptive and bad for performance because all threads wait in the barrier until the last one arrives. Well, every for loop, parallel for, has an implied barrier. So you wait at the end of this one, you wait at the end of the next one, and maybe that's not necessary. Maybe those loops are independent. And the barrier cost will start to, one of the things is the barrier cost increases quite a bit when you add threads. So it's a scalability bottleneck. So the recommended way is you have one parallel region from there to the end here. And then you have the OMP4, not the parallel for. Please don't do that. Then you have nested parallelism. That's even worse. So you have the single Pragma OMP4, and that gives me the cost of a parallel region only once. So I save, instead of n times, I have it once. So that's already a saving, and that's not small. And I can start playing with this no wait clause, if you have that situation. If they're all dependent, you probably want to jam them into one. I mean, that's another thing, minimize the use of your OpenMP pragmas. Try to make the work inside one pragma as much as you can. So this will give easier ways to glue things together, but also have the no wait. And one you can always put in, and sadly compilers don't do that for us. The parallel region always ends with a no wait, for good reasons, because you want to have all the parallel work completed before you continue. So there's always a no wait. There's always, a barrier at the end of the parallel region. Every parallel region ends with a barrier for correctness. But that means this barrier here is overkill. So I can always add a no wait in the last one. And unfortunately, compilers don't do that. Not so long ago, I asked one of those compiler people, do you do that for me? No, they don't. So take your control and add a no wait. Anyway, this is remarkably simple and can be highly effective. More basics. I just said that every barrier matters. You need them for correctness, but use them with care. And for safety, OpenMP gives you a whole bunch of implied barriers, and sometimes you don't need them. It's overkill. You can get rid of them. Locks and critical regions is the same. You need them for correctness, but don't sprinkle it. Once I saw an application, it had a very, very bulky loop, and almost the first thing in that loop set a lock, so nobody else can execute while one thread is doing it, and at the end it would release the lock, and you lose all your performance. So be careful with that. Use atomics where possible. The manual, the specs describe that. It's a simple operation. Like if you have like a one-line update, most likely an atomic update will be sufficient and applicable and not a critical region. Everything matters. Even when you run on a low number of threads, you may not see it yet, but as you increase the number of threads, those costs will start to matter. And again, profiling tools should help you find them, but don't leave anything on the table. Here's another popular one. You have the single region, and then there's a barrier, and that's all fine and good, but it's overkill, because that barrier, there's already a barrier at the end of the single region. That's all in the specs, but you may not notice that. So what I have two barriers back to back. Well, admittedly, the second barrier will be fast because all the waiting will have happened in the first barrier, but it still costs you. That second barrier is just overkill. It's not necessary for correctness, and it will just cost you performance, especially as you start scaling the number of threads. More things. Again, the no wait. I really like that. Very simple. It's not the first thing you put in your OpenMP code, probably, but once you have it running, you get the right answers, you can start looking for those kind of opportunities. The profiling tool will tell you where you spend the time, and for that part you see, well, maybe I can use the no wait. Always be aware, because if you have the no wait, then you can get data races. I mean, that's the downside. So that's why OpenMP by definition tries to be very safe. That's why there's an implied barrier. So you really need to know what you're doing, but later on I have an example of where I could. The schedule clause, it was discussed yesterday. It's a nice way to see whether there's the regular static schedule is not sufficient, and I have an example of that later on as well. Think about it. If it gives you better performance, it's clear an indication there's a load balancing issue in your application. These pragmas, these schedule clauses are fairly heavy. When they hand out work, for example, they have a lock to make sure that they do the right thing. So you initially pay a performance price when you switch from static to like guided or dynamic. But if the load balance is bad enough, you'll win. That's kind of the way it works. Nested parallelism was put in OpenMP 1.0. We desperately tried to get rid of it. You could have a parallel region in a parallel region. Don't do that. It's really, really very inefficient because of the heaviness and the barriers in the parallel region. Tasking is a much better way to handle those kind of algorithms that benefit from nested parallelism. Okay. Again, tasking is the modern way of doing things in that case. So I want to show a case study. Do more work and save time. That's always tricky. you initially start doing more work, then you better have a really good benefit in order to compensate for that additional work. But in this case, that was the case. And this is from real code. I mean, I didn't make this up. I have a parallel region, lots of code in it. And what it starts with, before the parallel region, it assigns a value to one element of a vector. And inside, a lot of code, but where the time was spent was an OMP4 and another OMP4, and there was a lot more code, and I cleaned it up. But this was the key part of that very big parallel region. And what we see is what looks fairly innocent. There's an OMP4, another OMP4, but there's some issues with it. First of all, I have two barriers because I have both OMP4. They will end with a barrier. That's not nice. And I have two loops. Every loop has a little bit of overhead, but certainly the OMP4 has some overhead, and I get that twice. Not a bad thing, but if I can get rid of it, that will be nice. The biggest thing here was the performance depends on two variables. The loop is n long. It ends with n minus, from 0 to n minus 1, but it's broken at a point called endpoint. And here's the problem. If endpoint is small relative to n, then this is a very short loop from 0 to endpoint minus 1. So this is where the overhead may affect you. If endpoint is large relative to n, this one will be your bottleneck, because that loop is maybe too short given how many threads you use. So there's a dependence on a thing called endpoint. And in this code, endpoint was sort of sliding. You would have multiple values of endpoint. You would always have cases where one loop was going to slow you down instead of giving you a benefit. And what I like to do in those cases is take the drawing board and start looking at what I'm actually doing. First of all, that was that one initialization at element endpoint. Then I blast -1 into a block of memory. I have the barrier at the end of the first OMP4. I blast -1 into another block of memory, and I have another barrier. That's essentially what's happening here. And the final result looks like this. And then I was looking at, well, wait a minute, what you're doing is you're assigning -1 to all but one element. Why don't you do it, and that's where the more work comes in, why don't you blast it in the whole thing and then correct that one value afterwards? Simple idea, really simple to implement with OpenMP. So that was the idea. I do this, that gives me, then it's only dependent on n, no longer on that endpoint, and then I correct. The one catch is, yes, you do need a barrier to make sure that this happens in this order and not the other way. So you will need one barrier, but you don't need two. And then that's the idea. Then the implementation is pretty straightforward. Now I have a loop from 0 to n minus 1, so an n long loop that initializes a to -1. Then I use in the single, I'm going to have, so here's the barrier. I know that, so I don't have to add that explicitly here. I'm relying on the fact that I know this one happens after this one. And then on the single here, I happen to be lucky I could use the no wait because what happened here was independent. And those simple changes are remarkably effective. And that's what I mean with take a step back, look at what you're doing, and see if you can do it in a better way. And that brings me to a case study, and then we're getting ready for the short break from graph analysis. And there's a benchmark called Graph 500, and for a while there was an OpenMP version of that, and I took it, and this is the structure of the code. It constructs a graph of a size. You give it the size, it will generate a graph, an unstructured, undirected graph. Then it will do a search in that graph. So it will select the key, it will randomly select the key, it will start searching, and it will do a breadth first search, and then verify that the result is a tree, because that should be. So there's a phase of searching and verification. And you do that a number of times, 64 in this case. For the benchmark score, which was interesting because I was looking at it to see if I could improve the benchmark score, only the search time matters, which is kind of interesting because, as you'll see, the verification part was almost equally expensive. But okay, it was about the search. It uses a parameter called scale to set the size of the graph. I used a very small one. This is what I just mentioned a little while ago. Yeah, we were seeing problems on large graphs, but I was trying to find out, well, what's the smallest graph where I see this problem? And the first signs were already on just 9 GB of memory. That makes my life a lot easier. So I picked that case, and I did that in our cloud, and I had a VM with Skylake cores. Okay. And I used our own profiling tool, and this is what that timeline showed, and I applied a bit of color coding here. So let me explain that. What you see in this tool is the time is from left to right. This is the single-threaded case. And what you see different phases. You see the graph generation. This spiky thing is the recursive quicksort going on. So before it starts the algorithm, there's some sorting going on. And then there's an alternating pattern. Red is search, blue is verification. So you have search, verify, and that's repeated 64 times for different keys. That's what the algorithm does. And here's the performance. Skylake, I only had 8 cores. Each core has 2 threads. Intel calls them hyperthreads. And that gives me a total of 16 OpenMP threads to play with. And that's good news, definitely good news in this chart. What I'm showing, the blue bars are the time, the search time, the real money in a way. That was the goal, to reduce it. The dotted lines are the parallel speedup. And the good news is that I could even successfully use those hyperthreads all the way to 16. You see a reduction in the search time. That's very encouraging, so it helps. The code as written wasn't as bad as it could have been, but the disappointing part is the total speedup. I only get 3.2, the best case. That's not much. Then you have the big question in performance tuning. How good is this? Maybe this is the best you can do, or not. So you start digging and doing experiments. And that's the way it goes with performance tuning. Again, I used our tool. I found several opportunities in the OpenMP part, and actually most of what I've showed before that were from that code, but they're fairly generic. For example, but that thing with that endpoint thing was in this code. So I cleaned up the code from an OpenMP point of view, removing all those inefficiencies. The single with the barrier was another one that was in this code. And each step doesn't contribute that much, but altogether it starts saving you time. And that's what I was showing. And look at what that did. That's the green one. And single thread performance was not affected. That's not a given, by the way. But in this case, it was the same. Then no gain on 2 threads. But then it started to get faster. This is a typical example of that overhead that's not so visible on 2 threads or 4, but as you increase the number of threads, it will become visible at some point, and clearly that happened here at around 4. So what you see at the end, it's about twice as fast. So we don't see much happening there, but when we look at the end, the search is 2 times faster with those changes. And that, of course, doubles my efficiency. But then the big question in performance tuning, are you done? So you start doing more experiments. This is encouraging. It looks like we have some opportunity to improve. And again, from a coding point of view, with very limited effort. That's what I said in the beginning. It's more about the insight that you have about what's going on than the actual typing in another pragma. And what I did, I looked at our timeline to see what's happening. And now we're looking at a run with comparing 1 and 2 threads. This is the profile for 1 thread. I've just shown it. And I don't care about that initial phase. I'm only interested in that search verification part. And what you see is it's faster. Okay, that's good. We know that. And we even see that even the initialization phase is faster, so that's all nice and good. This is faster, so we do have something to start with. But then I started zooming in. And what I saw was, wait a minute, this is the main thread. The main thread is fine, but look at those gaps. You start seeing the first gaps in the execution. And sometimes problems are dependent on the number of threads. It's always good to do multiple experiments. So I compared with 4 threads, and actually it got worse. Too bad. Okay. So the problem seems to increase as I add threads. And then I zoom in some more, and now what you see, there's always a gap in the red section here. And that's in the search. So there's something in the search, in the main thread, that causes the other threads to wait. That's what you learn from this profile. So the search has a bottleneck. And that's sort of summarized in this chart, where I look at the distribution of the CPU time across the threads. On 2 threads, I already see that the main thread takes way more CPU cycles than the second thread. And the same for 4, the main thread is way more expensive than the other ones. And then on 8, it gets worse and worse. And when you look at the ratio of the best time and the longest time, you see the ratio, the gap gets wider. On 8 threads, it's almost 2. So this is clearly a load balancing problem. I hope that's clear for all of you, literally exposed this way. Then you look at, well, what's happening in the code? Where's all that time spent? And it turned out to be, this is the part. I tried to clean it up. This has been cleaned up a bit. It's still pretty ugly, but that's real life. I mean, those are real codes. So you go through it step by step. You see there's a Pragma OMP4 there at the top. Let me use my tool. Here we have the OMP4, and at the end, we have the end of parallel 4. Okay. So this is one big for loop. The first loop, it's a nested loop. We see multiple 4s, has a fixed length. When you enter that loop, all the parameters there are known, of course, so it runs from K1 to old K2 minus 1. That's what's happening, fixed loop. Then there's another loop, but that has an irregular length because the loop start and end values depend on what you set above, and that depends on that outer loop. And potentially those are not the same values across all the values of K. Then within that loop, we have this part, and that has irregular control flow because there's this big if statement. If that equals to -1, then you do a lot more work, and otherwise you'll skip it. And even inside that, you have another if, and you do what's called the compare and swap, so that's an atomic operation. You do buffer copying. So whether this first if is true or false has a tremendous impact on the amount of work being done. It's a very clear case of a load imbalance. And that means for different values of K, you potentially do very different amounts of work. So that's the problem. Now, we have that default schedule. Default schedule tends to be static because static is cheap. It's cheap to do, it's cheap at runtime. You don't want to do that dynamic by default, but in this case, that's a bad choice. Because I know different threads do different amounts of work, so static is not good, and I use the schedule clause. If you use the schedule clause, please use, in this case, I use dynamic, but what I really do, I use the runtime version, because then I don't have to recompile my code. I use this clause, and the runtime will allow me to set through environment variables the schedule type and the chunk size. So it's a lot easier to do experimentation. So you set it to runtime because you don't know, or at least I don't know, what should I have? Guided, dynamic? What should be the chunk size? It's a matter of trial and error. I don't think, you can probably spend 2 years on trying to figure it out theoretically, but you use a thing called bisection. You start and you half, and fairly quickly you zoom in on what are the right parameters here. And I found in this case, dynamic scheduling with a chunk size of 25. Now, 25 could be 20 or 30, doesn't really matter. But it shouldn't be 1, or it shouldn't be 100. So how do you know that? Well, that's what I just said. It's called crystal ball, trial and error. You have to do some experimentation. That's just the way it is. But look at the benefit. The benefit now, that's the dark blue bar chart. Interestingly, it's small but noticeable that the single thread time goes up, because these dynamic load balancing schedules are more expensive. So there's no surprise that I lose a little bit of performance. But of course what you see, and again, now you see a big drop across all the thread counts, and at the end it's about, what was like 3 times faster now. So what I even have linear scaling here for all my 8 main threads, and then the second thread. This is why that curve, that red curve, speed up curve, is the way it is. I get full benefit from using all my 8 cores. Then I start adding the second thread in a course, and I get not a great speed up, but it does help. And yeah, so you get nice linear speed up. Altogether, you crank out 9.5x, and the search time dropped from 110 seconds to 37. So that's really nice. And when you look at the changes, it's really, really simple, because all I did for this last part was change the schedule clause. Always verify the behavior. I'm a bit paranoid, but sometimes that pays off. Like here, you see this was the chart with the original static scheduling, the timeline, all those gaps. I changed to dynamic. It looks very nice and compact, but of course, you don't know what you'll see if you zoom in. But instead of zooming in, I used a more scientific approach. I just looked at the CPU time per thread, and now you nicely see the balancing. So now I know I pretty much tackled that problem. Okay, takeaways. Well, there are always opportunities. Many applications have some opportunity. Just follow some of those rules, like don't have too many parallel regions, don't share data. Those are the first ones that you do. Be careful with things like critical region, try to replace them by atomic, because they're way more efficient. Those kind of basic rules are very general to many applications, and then you get into the more specific part that I was just showing. And always use that profiling tool. Okay, you're ready for the next part. This is all going to be about NUMA, memory. I'll start with the motivation. There was a bank robber in the 50s, 1950s. He got caught, and they asked him, "Why do you rob banks?" Well, the answer was astonishingly simple: because that's where the money is. The same thing is, I often talk about memory. Been doing so for a long time. Why? Because that's where the biggest bottlenecks are. Surely, when you look back at what I did before this break, that's more CPU focused. Get rid of a barrier, save CPU cycles. I wasn't really focusing on memory yet. That's what I'll do now. I'll have a different case study, but that's because the price you pay for not using the memory can easily be a factor of 10 performance loss, or 5 or something. CPU 2-3x is about as far as you can get. I mean, so the gain is very high, but the loss is also high. And this is the beauty of OpenMP is you need memory, you need some variable A, and it's in the shared pool, or even if it's in your private memory, you will just get it. That's really great. Makes programming a lot easier. Like the learning curve with OpenMP, we know that one of them is the scoping, the figuring out what's shared and private. And with MPI, it's you got to figure out where things are, and you have to mostly do that yourself in a way. Here you don't have to do that. But there are 2 cases that may hurt you when it comes to performance, and NUMA and false sharing. Now, false sharing, I'll say that again and again, is a corner case, but too often after I talked about this, somebody said, "Oh, wait a minute, maybe that explains why I have this performance problem." So I keep on talking about it, but I'll do it very briefly, just to make you aware of what could happen. One of the funny things is what I'm going to talk about has nothing to do with OpenMP. It's because we're using shared memory systems. You'll see the same in Java. I was talking to a friend of mine, he was here earlier this week, and he told me he found a case of false sharing in libc. I mean, So it can be everywhere. The fact is we use OpenMP and we see it, but again, it's independent of OpenMP, just that you know. It's because we're using a shared memory architecture. Now, fault sharing, what is it? Again, a corner case, but it may affect you. When do the bad things happen? Well, you got to have multiple threads, and they modify the same cache line at the same time. They're all contending for maybe one or two cache lines, so a very small portion of memory at the same time. This is when the cache coherence actually starts to hurt in a way. Because what will happen, that cache line will start traveling through your system. So each thread that needs it will have to get its copy into its cache before it can modify it. Meanwhile, what happens in cache coherence, conceptually it's very easy. Each cache line has a tag, and that tag gives the status. Like clean is great, you can just do whatever you want. But if it's invalid, it means you have the cache line, but you don't have the most recent copy, and the system will have to get you a more recent copy from elsewhere. That's essentially what's behind cache coherence. So you have states with the cache lines. Now, I'll just show you an example here. I have a parallel region, a very simple parallel region. I have one shared pointer, A, and within that parallel region, all that I do is I ask for the thread ID, and I have each thread initialize its own element. So I get the thread ID, and that initializes to 0. I don't know why I made a floating point, could equally be an integer, it doesn't matter, it's a bit confusing. But what I've just done is I created all the conditions for fault sharing, the ones that I just described. Because what I have a parallel region, so I have multiple threads. Usually the way things are stored, like if this comes out of a malloc, you have a consecutive block of memory. So A1 is next to A0. So what I'm doing, I'm accessing, at least for a while, depending on the size of the cache line, I'm hitting the same cache line because a number of elements of A are stored in the same cache line, and different threads try to update that. So I just created the conditions that I was showing on the previous slide. So at runtime, what will happen is the following. Let's say I just have 4 elements. The first thread, let's say the 0, you don't know which order things happen, but let's say 0 does that. It will need to modify A0, so it will get that line. If it doesn't have a clean state in its cache, it will get the line. That actually happens on the load instruction. The load instruction will do that will be the check. So you load a fresh line, and you do your assignment. Then maybe the next one is thread 2, but that's the key thing, it's all in the same line. So wherever thread 2 executes, it will need to get the correct value of that line before it can do the update. So that line will start traveling through your system. Yeah, you do need to update the coherence bits, that's not a big deal, but eventually, again, it all adds up. Because if this is in the heart of your algorithm, you do that 1,000,000 times, it will add up and you will see performance degradation. So generally, it is a function of the size. This is one reason why a long cache line is not always advantage, because the chance of fault sharing is higher. So like I said earlier, there's reasons to have long or short lines. And it's sort of a generic thing. And actually, when it happens, it's bad. You'll immediately see a bad performance. And interestingly, yesterday, Christian mentioned data races. When you have a data race, you have the ultimate fault sharing, because you're all modifying the same element. It's actually one of the reasons why, how you can detect the data race, your program will be much slower because of that, because it has a big impact on performance. There's always some fault sharing going on. That's fine, you don't care. But when it's really in that heart of your algorithm, that's when it starts to affect performance. And again, it's fault sharing. It's a corner case. NUMA is much more general. So I'll talk about NUMA the rest of this talk. And yeah, it's all going to be about memory and NUMA and all those low-level things that we need to know more about. So what's the thing? It used to be that NUMA was a luxury problem. Only those people that had very large servers would have a NUMA architecture. Then the whole idea came down, and now you even have some individual processors have NUMA inside, and then when you have like a 2-socket server, it's a NUMA box. So NUMA has become much more general, and therefore concerned to a much larger audience. The tricky thing is things just work. You get your data, and it all runs fine. And that's good. You first make sure you get your code running and you get the right results. And when we look at what systems look like today, you have at low level, they sometimes also call that like a chiplet. You have like a little computer as a node, or big one. It has a bunch of cores, it has caches, including that last level cache that talks to memory, and that's a compute node. And when you have multiple of those nodes, in a NUMA system, you glue them together through a cache-coherent interconnect, so that maintains the coherency across the whole system. And why would you do that? Well, first of all, it gives you a single system image. The system appears as a whole. You run top, and you won't see this underlying topology. The performance reason to do it, so that's the advantage in programming. It's a single system. From performance reason is that you add bandwidth as you add nodes. So you have a more scalable design at the memory level, and that's really nice. To us, in a way, this is the abstract way of looking at it. We have our threads running. They're connected to some portion of the memory. That's where my data is, and some magic connects it all together. That's the way to look at a NUMA system in a way. So with NUMA, the memory is physically distributed but logically shared. And shared data, as you have in OpenMP, is accessible to all the threads. And generally, for correctness, you don't need to know where the data is, doesn't matter. But of course, when you care about performance, you start to have to worry about that. So looking at the same picture here, let's say my thread is running in the upper left corner. If I get my data from the local memory, that's the best I can get. That's called local access. And by the way, when we talk about data here, the allocation level is at the page level. The operating system level is like 4K or 8K or 64K. It's at the page level. So the page is there in the memory, and I grab my data from it. That's, again, the best I can do. But nothing prevents this scenario, that the data is in some faraway corner in the system, and that will take longer. And that's really bad, because think about load balancing. You have threads that will have fast access, and some will have slow access, and they all wait for the slower ones. So you get all sorts of nasty performance things, and overall the memory cost is higher than it maybe could be. But the idea of NUMA tuning is very simple. You want to avoid that last scenario. You want to keep your data close to the threads close to the data that it needs. Now, in OpenMP, a decision was made to move threads, not data. Data is where it is, and the threads may move to it. And the reason is it's a lot cheaper to move a thread than data. Thread doesn't have much state. It's easier from the OS point of view. You just package the thread and you put it elsewhere. That's just a decision made in OpenMP. And I think a good decision. And the nice thing is, and Christian was one of the people deeply involved with that at the time, there are really nice constructs in OpenMP to deal with this situation. I think the committee at that time, when they came up with this, did a really good job to abstract it out in such a way that you don't need to be exposed to all the ugliness under the hood, but conceptually you need to be aware of things. And it's really powerful, but it's up to you. You can rely on the system defaults, but in generally it's your task to get it right. And when I say right, I mean about performance, not correctness. NUMA won't change the correctness of your results. So it's all about where's the data. And all the operating systems that I know, the common ones, not the specialized ones, they use a policy called first touch. That dictates where the data is allocated, and what it is, it's owned and allocated by the thread that touches the data, the page, an element in the page for the first time. Technically, for those of you that are into hardware, the ones that sets up the TLB entry in the TLB owns the data. Very simple rule, and it actually makes a lot of sense. It's the default on Linux and Windows and other OSs. Because it's the right thing to do for a non-parallel application. When you're running single-threaded, you want to have your data in your memory. And that's exactly what this does. So that makes a lot of sense. In a parallel program, that's not so obvious. Because what if one thread initializes most or all of the data? That will be the owner of the data, will be somewhere in the corner of my system, and everybody else will have to go and get it. That's a situation you'd like to try to avoid. And again, for the same reasons, theoretically, you can even have a lot of congestion on your network, but it's more the longer access time typically that affects you. Now, luckily, it's very often surprisingly simple to deal with this problem. And here's an example. I have a loop, and all it does, it initializes a vector to 0. If I would run it like this, by then, now you know, one thread will execute the loop, sequential part of my program, and that means all of A ends up in the node wherever that thread was running. Now, how do you fix that? Well, you parallelize that loop, and what you do, you know that with the static schedule, threads will slice up the iteration space, so they all initialize a portion of that vector, and then what you get is this situation. Let's say you're running this on 4 threads. They all get a slice of that vector in their memory. And that is at least a distribution of data compared to the other one. Of course, you need to have the data in the right place, and I'll get to that. But that's the basic idea. As when you initialize data, you make sure that the placement is done more or less correctly. And I say more or less because it's not always easy to have full control, but you can make it better. There's some tricky parts with this. What about I/O? When you read in all, that's typically a single thread activity. Your program startup, you read of all your data, and by then the damage is done. So a classical trick, highly effective, you look at your data structures that are actually going to absorb that I/O, and you parallelize them, you initialize them and parallelize that up front. It's redundant. It's not necessary for correct results, but it does define the layout of where things are. And as simple as it is very effective. So that's what I just said. Harder case is irregular data access. Graph analysis is an example of that. Things are all over the map. The best thing you can do then, and there's commands, actually the NUMA control command can help you with that, is to just spread the data across the machine, no preference. That means you probably have a longer access time uniformly across the board, but it's better than having it in the totally wrong place all the time. And I hope to do more work on that at some point and see what you really can get, but that's the general idea, is avoid having your data all in one node and everybody fighting for it. And NUMA control is a nice tool to actually do that. NUMA control is one of those Linux tools that allows you to predefine the way the data should be laid out. Certainly, if that gives you better performance, that's an indication that NUMA is affecting your performance. A word of warning, there's this function called calloc, very convenient. It not only allocates the memory, but it also initializes to 0. Well, don't use it, unless you do that in a parallel region. If you do this before your parallel region, you already defeated the whole purpose, your host. It's all in one node. So little things like that can make a difference. Okay. Now, what has OpenMP to help us? OpenMP, you know, it's all about where the data is. OpenMP has a concept called places. A place is a location in your system where you allow threads to run. And you can have multiple places, of course. You're in charge. You tell the system, I allow you to run here, but not here. Okay. And that, of course, with the application and the NUMA in mind. And you can have 2 ways. You can have a symbolic name, like cores, And with cores, you say, well, I want you to use the cores in my system to schedule, and you can actually add a number to it, so you can restrict it. I only want to use 8 cores, or whatever. You can go really low level, and that's what my example is going to be about. You're going to give those low level thread ideas. And I put that in just as an example. I wouldn't recommend doing it, but sometimes that's the best way, because sometimes also defaults across OpenMP runtime systems can be different. And this is sort of your way out to take full control, and I'll show you an example of that. You can't mix them. You can't have the symbolic name and the numbers, but that I think makes sense. Again, the date is where it is, and you're going to move the thread to where it's needed most. And you get 2 environment variables. One is called OMP_places, and that defines those candidate locations. Then there's a OMP procbind, and that defines the mapping onto the places, the mapping of the threads onto the places. What is that? Well, let's say you have more places than threads. The question is which one to pick from that place list. And that's what you control with procbind, and you get several choices. When you start going this way, I can highly recommend to set this environment variable, OMP display, and I always set it to verbose. That will echo the NUMA settings up front. It will echo a lot of things, but includes the places and the binding. And that's a great way to catch errors, because it's really easy to make a mistake with this stuff. So do that. You see it at startup, and of course when everything is fixed you can take it out again, but certainly while I develop, I use that environment variable all the time. That saved me several times. So what are the choices for places? You can have threads. That's all the hardware threads in your system. That's a very low level. You can go to cores. With the core, you say, well, yeah, even if the thread has multiple, even if the core has multiple threads, I don't care where you run it. Doesn't matter. And generally, it doesn't matter. But so that you give the scheduler a little bit more freedom to select where to run things. Then you can go a higher level, last level caches. That was that LLC that I've been showing a couple of times, the one that connects to memory. NUMA domains is a very important one, because that's at the memory level where you share the same memory, because that's usually what you care most about. So you can say, I have 4 nodes in my system. Each node is a NUMA domain, and that should be the scheduling unit, because within that things are fairly uniform. I don't care how you do it. Then there's an older one, socket. It's not even well defined. It used to be like the physical chip you put into the board. That's a very wide scheduling unit. I wouldn't know these days why you would use that compared to NUMA domain, but they're kept for legacy, I guess. Now, big disclaimer, otherwise Christian would also be angry at me. The abstract names are really the way to go. That's more portable in a way, more powerful. But I want to show you how to do things with numbers as well. Okay. So these numbers can be any sequence of valid numbers in as far as the numbering system in your system goes. And luckily, we don't have to spell out all those numbers. There's a compact notation. You give the start. It just generates numbers in a way. You give the start value, the total numbers, and the increment. And I'll show you an example here. For example, 0:4:2 means I'm going to have 4 numbers. They start with 0, and the increment is 2, so this will generate 0, 2, 4, and 6. And that's a very nice way to deal with those long lists, especially when you have a large system. So, and that's what you'll see me using. The places, just said most of this, but you can say places equals NUMA domains, and that'll be your scheduling unit. Essentially, that's going to be those nodes in your box. You can go down to this really low level. You can do, and there's something like this. And each one of this is a place, by the way. It's defined by the curly braces. So here I have 4 places. In the place, I don't give you any choice. You pick a place, it has to be, if you pick this one, it has to be on thread 0. So you don't give the scheduler any freedom, and sometimes is that what you want, and sometimes you want to give it more freedom. And the equivalent sequence is generated by this compact notation. I start with 0, the increment is 8, and I want to have 4 numbers. So this is equivalent and much easier to read and less likely to make mistakes. Proc bind, again, you define the mapping. You got 5 choices. You can enable it, true. I don't know what happens then. I don't like that kind of implementation defined behavior. You can disable it. Yeah, sure, why would you care? So in practice, what you use is one of these 3. When you go that way, primary means that you want the threads to be close to each other where the main thread is running. Close means that you want to keep threads close in terms, this is all in terms of the place list. The place list expands to a sequence of places, and within that, it should be close or spread. That's how these definitions work. And again, you'll see examples. So I want to use the cores in the system. I do this, and I want to push them out as far away as possible. So I say spread. And if I have like multiple nodes on the system, it will push them out to different nodes. That's what you get. Now, I need to revisit this example. I've been lying a little bit, only a little bit, but I had this example and I said, well, you got to parallelize this and then you get your data distribution. But it was wishful thinking. How do I know that the threads are actually scheduled like this? I don't. Initially, that's the operating system scheduler. With the NUMA stuff, I take control. So this was wishful thinking. I don't know what the OS does. Typically, the operating system would like to keep them together. So this is very unlikely to happen as a default scheduling. But now I have my controls. I set places to NUMA domains, so I have 4 NUMA domains in here, and I want to spread them out. That means they all get their part of the number of threads. So if I would have 8 threads, I would get 2 per node. Now, again, it's very easy to make a mistake. So there are 2 environment variables. You have the display env, and there's a variable called display affinity that will tell you at runtime what's happening, and that's really good to debug your NUMA cases. It was added later in a later standard. It's really useful because you can even control it. It has some bit of an API for the format and whatever. So that will tell you what's happening at runtime. Because threads may move. And again, use these, please, whenever unless it's very clear and you've got it all nailed down, but highly recommended. I'm going to finish with an example. And I'll do that fairly quickly because it's just an example, but I want to show you how you play with these things. Here's my favorite algorithm, multiplying a matrix with a vector. A equals B times C. This is the C way of doing it. I'm just taking the dot product of the rows of the matrix times the vector, and that will give me my result. That's embarrassingly parallel. All these dot products are independent. So theoretically, this is an embarrassingly parallel algorithm. Then I run it, and I'll give you the configuration in a minute, on a machine with 64 threads. And this is not a typo. It actually goes slower as I add threads. And it can't get any worse than that. You take an embarrassingly parallel algorithm, and it doesn't scale at all. I mean, that's like, like I said, couldn't get any worse. But that's also surprising. Why is that? Why is it so bad? And while looking into this, I found something interesting for those of you that'd like to know. Linux has a feature called automatic NUMA balancing. Red Hat put that in. And this is from the manual, but essentially what they do, they say they either move the threads or the data. And the last part I find interesting. And you don't get any information. I couldn't find out like what they exactly do, but they clearly thought about a NUMA problem and try to help you with it. And this is the hacker way of enabling it. I'm sure there's a control function to do that, but you either enable it or disable it by doing this. And that's what I did. I enabled it, and that's the green line. Well, that's nice. It's faster now. At least it scales. It's very disappointing still. We see a benefit going from 1 thread to 8, We see the performance in gigaflops going up. After that, it sort of flattens out, but it's sort of a freebie. I get better performance. It also shows there's a NUMA issue here, because clearly that has a big impact on performance. But still, in absolute sense, the performance is very disappointing. Now let's start looking at the system that we're using. And two of my favorite commands are lscpu and NUMA control. lscpu will show you a block like this. It shows a lot of things, but it will show you a block. And we have 8 lines. It means we have 8 NUMA nodes here in this system. And then what you see those 2 columns. The first column, it will give you those numbers. So it tells you that the first, in the first node, I have number 0 to 7 for my 8 cores. That's the first thread. The second one is the second thread. So the threads have a bit of a strange numbering. The first one is 0. The second one in that same core is 64 in this case. The reason is I suspect that it's very easy. If you have the sequence of numbers, you're just going to use that thread. So from a scripting point of view, it's kind of a little easier, but it's just something you need to know and check on the system that you have in case you want to go that way with the hardware numbers. Then there's output from NUMA control. NUMA control -H will show you the hardware latency table. And let me spend some time on that. That's a matrix. It's a symmetric matrix that's showing the relative cost of memory access. So it's normalized to 10 on the diagonal, which I found like curious. Well, why is that not 1? Turns out to be the Linux scheduler when couldn't deal with anything else than 10 and higher. So it's just a detail, but that's why it's not 1 but 10. Okay. So that's our reference, and then what you see, and again, it's a very symmetric matrix. They show all of it. But what we see, seen from node 0, 10 is my own latency. Then I have 3 nodes with 16. That's shown here. And I see 4 with 32. Now, one of those things is this is not a reliable number in the sense that you can say this is twice as expensive. It is more expensive. Again, this is actually the only reason they put it in, I suspect, not because of us, but because of the scheduler that needs to make scheduling decisions. So it knows, okay, I should stay close. So that's why. But we do see 2 levels of NUMA here, 16 and 32. So putting that all together, what we saw, lscpu gave us 8 NUMA nodes. We saw 8 cores per node. That was the 0 to 7. 2 columns. We have 2 hardware threads. And we have 2 levels of NUMA. That's what NUMA control is giving us. So when you put that all together, this is what the system looks like. Seen from a center node, I have my remote nodes with an access time of 16, whatever that may be. And then I have 4 more expensive nodes labeled 32. So this is a fairly complex NUMA architecture. Within one of those nodes, and again, it's all very symmetric. If you look at node 0, you have your 8 cores. Each core has 2 hardware threads, and these are the numbers. So that's how you can completely dissect the topology of your system and figure out what it looks like from a NUMA point of view. Knowing that this is a pretty bad NUMA system in a way, let's go back to the drawing board. We have our OpenMP code, and there's nothing wrong with that code. The code as written is perfectly fine from an OpenMP point of view. It's the way you want to do it. But it's not NUMA aware. I did not take NUMA into account at all. And by now, you should know that that means your data initialization is not okay. And I didn't talk about that here, but the data initialization in this case is sequential. And I need to make it more NUMA friendly. So this is the original data initialization. I initialized the vector. It was A equals B times C, so I initialized the vector. I initialized the matrix. And Paranoid Me also initializes the result vector, which is redundant, but it has the same NUMA effects as when you load data. Because typically you can only modify an element when you have the cache line. Well, if the cache line has to come from far away, it also happens on the store. So small effect, order M, so it's not really worth bothering. The big one is the matrix. The matrix needs to be separated. So what you do the way you do it, you go back to the drawing board and you look at the way the algorithm goes through the data. Well, it takes rows of the matrix, and the static schedule, as you know, takes chunks of that. So essentially you process blocks of matrix B that take the dot product with C. And what I need to figure out is how do I distribute those blocks of the matrix across my system. The rest is more, I would more like a bit cosmetic, but that's what I do here. And remember here, the matrix is my real target. I should maybe remove the other stuff. The matrix is my target. I do the same as I do in the algorithm. OMP4 over the outer loop, over the rows with a static schedule. Then I know that the initialization happens the same way as my algorithm uses that matrix. And I can do that because this is all static. As I said a little while ago, when things are more dynamic, it gets much harder. But I can do that here. I also, one of the questions is vector C. What do you do with the vector here? Everybody needs it. They need a whole vector. And it's very tempting to think, oh, I'll make a copy. We wouldn't do that. Copying data is expensive, takes more memory, usually more bookkeeping in the code around it. And this is where caches will help. C is order M, single order in a way. So caching will help. I mean, these level 2, level 3 caches are large enough to hold very large vectors of C. And the first time you go through the first row of your block, yes, you'll have to load all of C, but the other rows will have it in their cache for sure. So I wouldn't bother with C. But what I did to help it a bit, I still split it, so at least a portion of C is already in the right place. Again, small effect. You probably can't measure it, but it's just a little, as you're working on that, why leave it on the table? But it's not critical for performance. Again, the big part is this B here. Now I'm going to run this new code with a new initialization, and I just want to place my threads evenly. This is just as an exercise, as to show you. And for some reason, I want to use the first hardware thread of the first 2 cores of all the nodes. That's, again, just an example of how you play with these settings. Let's say that's what I want to do for some reason. This was my little diagram. So what I want to do in every node, I want to use these 2. How do I accomplish that? Well, I'll go back to my full system. So in that system, in case I run on, on 16 nodes, 16 threads, this is the distribution that I want. Always those 2, again, or those 2. I could pick other combinations, it's fairly symmetric, but again, for the sake of the example, this is what I want to do. How do you accomplish that? Well, I define my OMP places as follows. Because let me go back a slide. So what I need to do, I need to figure out a way to generate a sequence of numbers, 0, 1, 8, 9, and so forth. That's what I need to do. And I'm using that shorthand notation. I start with 0 here. I have 8 numbers with an increment of 8, so that's going to take care of the even numbers, and this one's going to do the odd numbers. So this exactly expands to that list. And in that way, you get what you want. These are all my places. I got 16 places here. And when you look at those numbers, that exactly corresponds to what I want to have. Then I put the binding to close, but since I'm using 16 threads on 16 places, the binding doesn't matter because there's nothing uncertain. You just map them directly, but again, for the sake of the demonstration. And this is the new performance. This was the old best performance, the green one. There's a little bit of funny thing in between. I guess that this system has 2 layers of NUMA. I didn't really take that into account. But if you just look at the starting point and the end point, you see that you get more than 30 times faster. Now, admittedly, this is an easy case. Sure. But it shows you the potential and what you can do by setting those environment variables. So altogether, compared to the best one that I had here, it's more than 20 times faster. When you look at the breakdown of the numbers, it's kind of interesting. In this little table here, let me see, I have single thread, I get the same performance. First touch optimized or not, doesn't matter because there's no parallelism. When I have my basic algorithm, I don't get more than 8 gigaflops, and with first touch, I get 113. And that flattens, as we saw. So 64, I can still get 8 without first touch, and then I go up to 175. So that gives me a factor of 22, roughly, and about 30, more than 30x overall improvement. That's just sort of the carrot for you to think about NUMA. We see that all the time. Again, this is a lucky case in a way, an easy case. There are harder cases. But what I would say, data and thread placement, they matter a lot. I hope that's clear now, or could be. Think about first touch. For example, when you have a parallel region, you malloc inside that parallel region and then initialize that block of data by the thread executing it. Then you're done. It already automatically has access, because one of those things that are not all of you may know, but malloc doesn't do anything other than reserve space in a table. It only happens when you start using that data. So you initialize it, that's when the page allocation takes place, that's when the layout is determined. So by thinking about that in a local way, you already avoid a lot of the NUMA problems. And that's another reason why I say use private data as much as you can, because that's automatically owned by the thread and should be in its local memory. Okay. OpenMP has pretty nice support for NUMA. As simple as it is, it's quite powerful. Things are added, like, for example, the places list was extended as architectures got more involved. The early OpenMP implementation did not have NUMA domains, for example. So wrapping it all up, a long talk, and I'm sorry for running late. If you follow what I said, I think it'll help you getting better performance. Yes, it is frustrating, can be, and it's an iterative process. Just don't give up. And if something gets you in the way, think about NUMA or maybe fault sharing. Hopefully not both. And think ahead. Don't leave anything on the table. Think about what may not be an issue on 4 threads could be on 16 or 32 or whatever. So don't leave anything on the table. I've said more than enough. It's time for a break. If somebody comes to you and says OpenMP does not scale, tell that person it's bad OpenMP that doesn't scale. All right, thank you very much, and good luck with the remainder of the workshop. I'll be here today and tomorrow, sitting in the back, so we can always have discussions if you'd like to have that. Thank you.